see what the coffee does.
Would like to invite you to take your seats as we just prepare here to get started in just a moment. Thank you all for joining us tonight at the AIM Center as we launch our Fall Colloquium series, Moving, Making, and Meaning. We're excited to have you all here tonight and look forward to an engaging evening together. In addition to those in the room, we have some participants joining us tonight on Zoom. So we invite you, if you feel comfortable, you can allow us to see your faces by checking video on. If you prefer not to, that's okay as well, but we're happy to see you and invite your engagement and participation in the session as well. At the end of the talk, we'll have some opportunities for questions and some feedback. And so, hello, Chris. And so you'll be invited to participate with questions from your Zoom location as well. And just as we begin tonight, we want to recognize our AIM scholars who are pursuing their master's degree programs here at Fresno Pacific University. If you are a returning AIM scholar, would you please raise your hand so we can acknowledge you? Yeah, congratulations, welcome. If you are a new AIM scholar, would you please raise your hand? And congratulations to you and welcome. Glad to have you here tonight. And to all of you here, welcome. This Colloquium series is devoted to perspectives that emphasize the core role that human activity plays in learning. The learning sciences suggest that learning occurs through a series of dynamic interactions between individuals and their social and physical environments. So for science, technology, engineering, arts, and mathematics, known collectively as STEAM, scholars and teacher educators, teachers, learners of all ages are broadening notions of what it means to think and learn and engage in these disciplines. So in this Colloquium series, we'll explore questions around these ideas as we examine how human activities such as moving and making contribute to cross-disciplinary engagement in mathematics, science, and the arts. So tonight we hear from guest speaker Dor Abramson, who's professor of cognition and development with a secondary mathematics appointment at the Graduate School of Education at UC Berkeley. At Berkeley, Dor runs the Embodied Design Research Laboratory, which designs, builds, and field tests learning environments that foster K through 16 students' inquiry-based learning of mathematical concepts. Dr. Abramson has received a National Academy of Education Spencer Postdoctoral Fellowship and National Science Foundation Awards, and has published dozens of peer-reviewed articles in leading educational research journals. He is also co-author of a chapter on embodiment and embodied design in the Cambridge Handbook of the Learning Sciences. Dor is also an accomplished cellist. Tonight, Dor will present his talk, A New World, Educational Research on the Sensory Motor Roots of Mathematical Reasoning. Dor's presentation will survey results from several recent design research studies that have used eye-tracking techniques to capture the moment at which a student first sees the world in a new way. So Dor, thank you for joining us tonight.
On the left matters. 0, 8, 2, 8. I can do that. Okay. This might actually work. Wow, it worked. Excellent. So good evening, everyone. Everyone here, everyone there. I'm not sure where the Zoom people. I'm seeing you there, but you probably, the camera is somewhere else. Technology can be confusing. Thanks very much, Paul, and the AIM Center. Oh, is it following me? Thanks very much, Paul, and the AIM Center for inviting me. I'm so glad to be here, and I was telling everyone about my Amtrak trip here. Whoa, I thought I'd go by car, but then I said, hey, why lose, 6 hours work, right? So I came, it's fantastic. Okay, no, Amtrak doesn't sponsor this, but anyway. So I think I'll begin by splashing on you some text here on the wall, and if it makes complete sense to you and you don't contest it and it's old stuff, or if you find it offensive and don't want to be here, then just get up and leave and we'll remain friends. But hopefully there's something interesting here for you. So mathematical concepts are grounded in sensory motor perceptual structures that emerge spontaneously as pragmatic solutions to the problem of efficiently enacting ecologically coupled movements. So I put it up there because it looks like impossible. What the heck does this guy from Berkeley mean? But we'll come back to the slide at the end, and so then you can Yelp me if it makes sense to you now. Okay, no one's left. That's good. Just came all the way, I guess. Yeah. But maybe I'll just try one more slide on you guys, and that's this one. And it's kind of getting to the essence of what we're doing and why we're doing it. So as Paul said, we're trying to engage different ways of thinking about the mind and what the implications are for teaching and learning. The brain is not a computer. For a whole, well, during the 20th century, certainly the last half of the 20th century, people have been telling us, so the brain, like it gets inputs and then it like abstracts them into these, they're like almost like digital-like symbolic propositions, and then it processes these, and then you come to inference, and then it kind of outputs, and then you have action. But all the work goes on in here and has nothing to do with the input. It's sort of input agnostic and output agnostic. It's just churning stuff, and it's not related to the modality, sensory modality, the hearing, tasting, feeling, everything.
It's not related to the kinesthetic.
And other sensory modalities. It just goes on there like a CPU. People were very much enamored with this metaphor of the brain like a central processing unit that has nothing to do with the situation in which it's operating, as if that's something else. And that's like it's called a dualist look at the world. The subject and the object are separated, and we need to teach people how to do things in their heads separate from the world. Just earlier, folks here at Ames were telling me about kids counting with their fingers. So I ask you, are fingers in the head? Are they in the world? Are they in between? Where are they? And why do we do that? The brain is not a computer. It does not process abstract symbols or prepositions. The act of thinking mobilizes the same mental faculties and experiential modalities by which we function in the natural and sociocultural environment. We don't have another brain. We have just this one brain that, for evolutionary and sociocultural reasons over the millennia, we have co-opted. Steve Gould calls it acceptated. It's like adapted, accepted. It's not adapted, accepted. We've co-opted these faculties that we have for just walking, talking, being, doing stuff into a way of thinking. And we've made mathematics, for example, into a discipline unto itself that we can talk about as a thing that's disconnected from the doing of everyday world. But that doesn't mean that we have suddenly a new brain that's doing it. It's the same brain that does the walking, talking, moving, counting. It's the same brain that does these things. And so we need to understand how we operate in the world and how we learn physical skills, how we learn social skills in order to understand how we do mathematics. How we think, therefore, depends on how we know to move in the world, how we know to operate on various objects, what tools we have mastered, what languages we speak. Different languages have different access to mathematical ideas. If you speak, for instance, Chinese, then you have less syllables to articulate when you count. That means that in a same expanse of time, you can utter more number words as your fellow American, not to speak fellow Israeli, not to speak fellow, say, Jordanian, where it's even longer words. You can just crush more into that time. Or if you speak Chinese, you might speak differently about what a fraction is, whereas we say, I don't know, 2/5. In Chinese, they say, of 5, take 2. It matters how you talk. It matters how you count. You will learn differently. The very tools we use, if you learn to work with an abacus or with a calculator, that matters. These tools really change the way that we think. As such, educators can affect students' cognitive by shaping their sensory motor experiences with dedicated objects. Because if all of this is true, it's like, you know, Pascal's wager. Maybe it's not true, but if it's true, we better be doing a good job creating environments, creating artifacts. I feel like I'm preaching to the choir here. I mean, everyone's here because they want to work with Ames and with Fresno Pacific, et cetera, and working on developing tools, working on developing activities, working on developing professional practices to facilitate, to guide children as they engage with these tools, as they build first meanings with these tools, as they enculturate these first meanings into the discipline of mathematics. So that was a lot of words, and I won't be slapping on any more text like that. I just like catching you while you're still alert, right? And before you're thinking about rush hour and picking up your kids and so on. So now I need to peep here because I don't remember what the next slide is. Oh, well, that's easy. There's nothing on the next slide. Okay. So people love Venn diagrams and talks, and so I'll be Venn diagramming you for a moment. It's just so helpful to bring things in. So we are now at a very exciting time to be in the learning sciences, in particular for people who are interested in mathematics and science education, because 3 historical movements are now sort of come to a head and are converging. And they are theory and technology and methodology. And I want to explain to you what I mean by that and what these things are and how they are converging. So in terms of theory, I've already slapped the text on you, right? We're going towards something called embodied cognition. If in the 20th century, we were very much talking about computational models of the mind and sometimes referred to as cognitivism, sort of representations in the head, all the work goes on in the head. Yeah, there's input, yeah, there's output, but the thinking is essentially nothing to do with the modalities of being, nothing to do with the senses, nothing to do with the action. It is non-modal, or the word they use is amodal. A is as in not. Amodal. Thinking is amodal. You know, why bother with all these? What does it matter how you teach? As long as they learn, we can just tell them and then they'll know. So we're moving away from that. There's a sense of a paradigm shift in the cognitive science, in the philosophy of cognitive science, towards something called embodiment, or it's like, well, there's a new name every other year almost. It was just embodiment, and people say, yeah, but it's also, you know, body's extended through the, okay, so also extended. So then it was, but you know, it's also enactive, because actually the doing is the knowing. Okay, so also enactive. And fortunately, this was all E words. And then they said, oh, but it's, you know, it's within the ecology, so it's, but it's also embedded. So it's like every year you have to learn this new E. Luckily, they're all E's. Right now, people talk about the 4E, like the 4 E's. So recently, there was an international conference of the International Society of the Learning Sciences. It was held in Lyon, in France, and it was all about the 4E cognition. And there's the Oxford Handbook of 4E cognition, etc. So we sort of stabilized at 4, and so some people sometimes say to me, why is your lab called the Embodied? Don't you know that now it's also extended? And I was like, guys, just give me a break. This back then was called that. Am I going to update my lab's logo every year? So embodied, we're moving into this other paradigm where we're rejecting, see, people tell me I should never advocate in talks, always be like a scientist. We are evaluating this alternative paradigm in the cognitive sciences. And as learning scientists, and specifically as design-based researchers, we are evaluating the purchase, the traction, the advantages of this alternative way of thinking about thinking for the design and the teaching and the implementation of designs and the study of human learning. So we're into embodied cognition, and the idea again is that thinking is constituted in the sensory motor imagination. Okay, thinking is sensory motor imagination. It doesn't necessarily simulate what you're doing, because it could do also impossible things. My daughter's learning now about imaginary numbers. So I was like, right, it's not real, but they're kind of like there. So are they real or not real? Oh no, wait, the word real already means something else. So theory, embodied cognition. But we're also talking about technology. Looking around here, don't need to be an ageist, but I know there's some people around here who started out with DOS, right? And first learned with BASIC and Pascal. I learned with Pascal. And wasn't that kind of annoying that you had to get every semicolon right in order to make things even work? But that was with our everyday computer. That's how you needed to interact through a keyboard. But then other graphical user interfaces came along, and suddenly, oh, I can click on things. And in fact, I don't need to click on the keyboard. I can click now on the screen, right? And then other kind of natural user interfaces came along. Now that things recognize my gesture, I recognize my voice, and I can dictate. The world is becoming kind of easier. These interfaces are so seamless and porous. But actually, sometimes in these embodied interaction interfaces, sometimes as designers for mathematical concepts, we actually want to build things that are not seamless, because we want children to learn to move in new ways. We want them to figure things out. So unlike in industry where they want to build things as seamless as possible, you don't need to think, you're just kind of doing it, it happens. Often, as you know, as designers, we want to bring children towards some kind of sticking point, some cognitive conflict, something sensory motor conflict, if you will, something they need to figure out. So we're talking about remote sensing, and we're talking also about other technological advances that take us into new methodology. So for methods, I'm going to be talking about multimodal learning analytics. I'm sure some of you have what they call Fitbits, right? We can know the quantified self. We can know more and more about ourselves. We can measure aspects of our being that where other sort of just tacit or stuff goes on. Like I believe my heart is beating now. I don't know how much, but all kinds of things are happening, and maybe a certain galvanic skin reaction. But some of these things, maybe many of them, more than we believe, are related to learning. And if we could have access to them, maybe we could know more about the learning process. I'm just reviewing a paper now that has in it a figure that looks like something out of the Matrix. Kids are sitting in the classroom, and they all have these sort of wires and things connected to them, and they say these are non-invasive multimodal learning analytic measurement tools. So it's going in all kind of interesting places. At least it's not invasive anymore, right? But if we can know where kids are, for instance, looking, that could maybe help us figure out how they are seeing the world, right? In my very first slide, I used that phrase, sensory motor perception. I have 4 objectives for today. I might even remember some of them. One of them is I want you to know what I mean when I say sensory motor perception. The other one is I want you to have a first-hand experience of how a sensory motor perception emerges and how it can change. And I want to say why sensory motor perception, that very notion, is related to mathematics learning. And I want to show you data that I believe support the argument that we could literally see the moment that a new sensory motor perception was born, a new way of seeing the world, a new way of accessing displays, a new way that ultimately is relevant to mathematical knowing. So our lab's work, the Embodied Design Research Laboratory, is situated within these 3 areas, as often we do with Venn diagrams. You know it's coming because, right, the middle is empty. So we work with the, and evaluate, we inform by and hopefully contribute to the theory of embodied cognition by developing embodied interaction tools related to what we believe is mathematics learning. And we use various methods, including, as Paul mentioned, eye tracking, in order to figure out and characterize and therefore support and iterate on our designs for mathematics learning. And so that's what I'm talking about over here. And we have a catchphrase, which is learning is moving in new ways. And it has actually two meanings. It's a bit of a nerdy pun, I guess, imagine. So one of them is that we think that when people learn to move in a new way, that is when they start to learn a new mathematical concept. So we're looking at how people learn to move in new ways. So the very learning happens as a new kind of way of moving in the world. But then there's the other meaning, which is that the phenomenon of learning, the construct or the object of inquiry that so many of us do when we study human learning, is in of itself moving in new ways. We are moving towards embodied ways of thinking about this construct. So learning is moving in new ways. Where do I go from here? So we've recently changed the look of my, as I'm preparing this, we have now, we moved from Drupal to WordPress, so it no longer looks like this. But essentially, this is the lab's website, Embodied Design Research Laboratory. And yeah, learning is moving in new ways. And if you go to our website, you can read our stuff and read about the projects. But I'll be speaking specifically about a project called, we used to call it kinematics, but just think of it as the mathematics imagery trainer. And that will be the context in which I will speak about our formation of new constructs, something called an attentional anchor, okay, with the letter A, from attention, attentional anchor. I'll be speaking about that. All is in the context of designing and investigating, evaluating how students learn and how people teach with these kind of embodied interaction tools. Okay, so here's a weird slide. This is a photograph of my dad, actually. So my parents are celebrating today their 59th anniversary, and we phoned them and sang for them, happy anniversary to you, it's kind of dorky, and sent them flowers. But I'm putting this here because my dad is a surgeon. He'll be 90 in December. Don't worry, he's not operating anymore. He was just visiting in San Francisco, the UCSF robotics place, and just messing around with them. But the reason that he's up here, because I want to tell you a bit of a story, and this goes back, I guess, 40 years ago. My family, I grew up in Israel. My family went down to Sinai, to the Red Sea, and my brothers and I were scuba divers, skin divers. We'd done that kind of stuff a lot, but my dad had never done that. Now, if you've never scuba dived, you look, you say like, there's nothing there, right? You don't know that underneath this, there's a whole new other world. So we said to our dad, he'd never scuba dived, even though he grew up in South Africa, literally on the sea, but he'd never like gone under and seen a reef. We told him he really should. He used to be a very kind of serious guy. We said, let's go ahead and do it. We gave him a mask and snorkel, and he actually went under there. And come on. It's funny, PowerPoint is acting interesting. It's like in little saccades instead of smooth. All right, it's supposed to be smooth. He went around, and then he came out. Now the thing is, he walked out, and this Sears guy looked at us. We'd never seen like that, with big eyes. His jaw dropped, and he said to us just 3 words: "A new world." Because what he had seen is the reef under the water. He'd never seen it before, okay? And was for him a totally new world. And obviously, at some point, some analogy is going to come along. All right, what's he telling about his dad? He was seeing the environment in a whole new way, seeing the sea in this case in a whole new way that he had never seen before. We weren't there underwater to see him do that, and it's kind of a pity, because it would have been nice for us to see how he is seeing the coral for the first time, right? And I want to suggest that this is a kind of analogy to the work that we do, many of us do. We want to see how other people are seeing the world in a new way for the first time. So here is this is now like a student sees a situation a new time. So, oh yeah, I can do it. I get it. Oh, I never saw that before. I could never do that before. This is new for me. But at the same time, oh, sorry, and this can inform our knowledge about how people learn. If we can know how they are doing that, and in turn that will help us say how should we teach. But in order for all of this to happen, we need to be able to see these things happening. And the question is, how can we see learning? What does it mean for us to see learning as it is occurring? So all of this brings me to the talk today that finally can open up here with a jittery curtain. The projector is having a bit of Tourette here. Okay. So yeah, a new world, educational research on the sensory motor roots of mathematical reasoning. So talk to you about sensory motor perception, what it is, why I think it matters to mathematics learning. Okay, so the work we do in the lab is about design and design-based research. But in terms of design, we see ourselves as continuing a tradition that started with Friedrich Froebel. Does anybody know what the meaning, what the significance of that year is? 1837. Quiz. Nah, people don't usually know. How would you know? This year was the very first day of kindergarten. There was no such thing before. It was like, okay, kids are little adults, let them start teaching them how to do stuff. And he was the first one, Friedrich Froebel, to say, no, we need it's like a garden. It's Kinder is children in German, Kindergarten. We need to cultivate these children. And he was the first to come with a very systematic pedagogical regimen that included objects such as these, which kind of look familiar, right? Because it looks like stuff that came later, like Montessori and others. And he called these things gifts. So on, I think it's day 1, you give this, or like, this is gift number 1. It's like a ball of yarn. You want them to feel spheres. And he based his entire pedagogy on that. And I'm sure some of you, or many of you, learned with, or even teach with these kinds of things, right? These things are familiar. We often call them manipulatives, or what have you. This is a more advanced one. This is Seymour Pappert's turtle, the original turtle, before it went only on the screen. I call this work embodied design. And the idea is that we, as a design, we are constructing means, like ways for the children to construct meaning. Okay, we're constructing means for the children to construct meaning. I first coined this term when we created the lab, I guess, in 2005, but first in publication in 2009. And the idea here is that children should first experience, I'm ad-libbing because the things aren't coming up. Oh, here we are. They should experience things first, and only later they should analyze what it is that they are doing. I want them to have first-hand experiences, and only later see these moments as mathematical and mathematically significant through our intervention. And all the question is, what should they first experience? So we're going to begin by asking, as such, how do people learn, and therefore how should we teach? So how do people learn? So I need to bring you to this, I need to bring you back to this phrase. If I want to explain to you what I mean by sensory motor perception, let's start by saying what is even the difference between sensation and perception, and later we'll bring in the motor, all right? So I'm sure many of you have seen these kinds of things, these ambiguous figures, or two ways of seeing them, right? You can see it as two profiles, or as a vase, right? But, all right, this is getting frustrating. It's slowing down more and more. All right. So you've seen these ambiguous figures before. The Necker cube, you can see it as if it's coming at you or going away from you. And of course, the celebrated duck or rabbit. I'm sure you've come across these things before, where it looks as like one thing or the other. Now, the point about these images is they help us see the difference between sensation and perception, because one and the same image is coming at our face, and yet we can make different sense of it. So that's the difference between sensation and perception. And in these cases, it's right. It's not what you look at that matters. It's what you see. It's or how you see it. Perception is constructed. We don't just make copies of the world. We need to figure out what something is, and we make sense of it. What you see is how you see. It's not the case that this is a duck or a rabbit. It could be either, depending on how you look at it. So this is one difference between sensation and perception. And okay, so are mathematical perceptions also constructed? What might it mean, therefore, if we want people to see the world in a new way, if we want them to see proportion, for example? Where would that come from? What is the stuff that we need? What are the ducks and rabbits? What are the images? What are the displays? What are the things that we need to give them? And how will they come to see the world the way we see it, right? The special way of seeing it. So let's look at one way of seeing the world in a new way. Here I'm with my daughter, and we're actually learning about the commutativity of multiplication. So like this is 2 times 5, but then this is, well, 5 times 2, right? 2 times 5, 5 times 2. So this is an instance where you are actually making the things with your hands, and at the same time changing how you look at them. So it's a very kind of borderline case, because you don't have manipulative, it's the hands themselves. But it's kind of one way of getting at these kinds of notions I'm talking about. And it's different from these here, right? So when I spoke about the duck rabbit, there was nothing to hold. There was no actual thing there. But it helped us separate between sensation and perception, because I'm trying to explain here what is sensory motor perception, right? The duck helped us do that. But how can we bring in the motor, right? Motor action as separate from sensation move. Here it's kind of difficult to do it, because the hands themselves are the objects we're looking at. So I'd like to look at something else. That one is hands off. This one is sort of hands in. I want to suggest that we look at things like tools. So like the manipulative, the things that we bring to students, and to see how they can come to see them in new ways. And I've chosen this one for a reason, because it's such an essential paradigmatic tool. It's something so simple. And in fact, you can make it bigger, and it just so happens that I have one here. Okay, and here it is. Now, okay, so the reason I'm going to do with you a quick exercise in phenomenology, right? So I can say just, what is this? And everybody says, duh, it's a red pencil, a big one, right? And yeah, and you could say it has you could tell me all kind of stuff about what it is, and right? But I'm not talking about that. I'm not talking about dictating mathematical or dictating concepts and telling what things are. I want to bring you to a place where maybe you're not used to being and thinking. I want to bring you to a place which is about how you relate to this object. How is it that you relate to this object, okay? And so what I'll ask you is, how would you engage this object if you had this thing here, a pad, right? May I ask you? How would you take this if you had to use it on that medium? Right, okay, exactly. So it's just down there, right? It's that. But what would happen, though, if I bring something else like that? How would you use it, Steve?
Oh,
of course, the idea is to pop.
I would definitely pop it. Yeah.
Yeah.
Absolutely.
All right. Okay. So we moved fast from this to that. Okay. My point here is that it's still the same object, but the way you oriented towards it and towards the environment changed dramatically. All right. It's the same object, but I'm talking about how you are orienting towards. I'm talking about your sensory motor perception of this object. How about this one? People want to pantomime for me? How would you do that? Yeah, it's very different. Again, it's the same, but how could that be? It's the same object, but we orient to it very, very differently. And of course, all right, so this is a poor ladybug stuck in the water. Can you pantomime? How would you use a pencil to help her? Thank you for being so gentle. Yeah, so it's the same object, and yet you relate to it in such a different way. So it's like the duck rabbit in that. I felt I was kind of losing you for a moment there, but it's the same kind of idea, but only here we're bringing in the motor. And yeah, we could play this game until the cows come home, right? But the question is not what is it, it's how do you engage this, right? And Franz Mexner, researcher I like, he says, I hope this doesn't disturb you here, this overlay, affordances, or like the ways of grabbing and doing things, are not only perceived as properties of the affording object, by way of educated phenomenological sensitivity, which is what we're doing, educated phenomenological sensitivity, we may also experience the specific way our body is related to the objects of our interest. So I deliberately put this object on the screen. I only select a few of you people to actually touch it, but then I ask you to mime it, specifically so that you experience this. I've severed the object from your own body, and you can feel in your body a different way of orienting towards that. You literally see it differently according to what you're trying to do. And all of this is coming to a head in that we want to create opportunities for students to see the world in a new way by way of creating activities where they need to orient in a new way towards the world, such as ways related to learning proportion. So what this is what you do with it. And the question is, where will new mathematical meanings come from? So now we've spoken about the sensory motor, sensation, perception, and the motor. The sensory motor perception is the way that you see an object towards handling it in a particular, with a particular function, with a particular objective. That's a sensory motor perception. And this is rooted in work going back to Piaget, of course, sensory motor intelligence. All right. So where are we in our, I almost said Zen, our Venn diagrams? Let's speak a bit quickly about theory. So this will be very quick because I've already said a few words to you about it. So people used to think that the mind or the brain works in this way where we get input from various sources of touch and taste and smell and sight and hearing. And then all this information goes into the head, and then we process that information in the brain. I promise you this is smooth usually. Yeah. And then we send some command to the hand that then, or the body, that then falls into action. But that's the old paradigm. The new paradigm, we think rather that all of this is happening at the same time, okay? The input, what you might call the input and the thinking and the output, it's all the same way. There isn't a special mind here that's processing abstract units. Thinking is imaginary engagement with the world. And just so you know, this is not some crazy stuff. This is Terence Tao, professor at UCLA. He got full professor at the age of 24. Ouch. And when he talks about his work, he says, this is a quotation, for evolutionary PDEs in particular, I find there is a rich zoo of colorful physical analogies that one can use to get a grip on a problem. I've used the metaphor of an egg yolk frying in a pool of oil or a jet ski riding ocean waves to understand the behavior of fine scales, and etc. This is how people think. We know that going back almost 100 years from interviews with leading scientists and mathematicians. People think in images. People think with their body. People think with their imagination. And I just don't know if we're doing that enough in classrooms. So I operate from this theory of enactivism. And in a nutshell, 2 points. So I've really spoken already about this. There's never just perception. Whenever we see something, perception consists of perceptually guided action. We see things in order to act with them. The looking at the world, the hearing the world, the smell, it's always goes back neurally, evolutionarily, phenomenologically. We always engage with the world in order to try and get something done. And the second point here is that cognitive structures, what you might call concepts, where do they come from? From things that are repeated, sensory motor patterns that are repeated as you try to do things more and more that enable action. Yeah, that's going back to here. So concepts emerge out of these repeated sensory motor patterns that enable action to be perceptually guided. As a designer, I ask myself, what are the cognitive structures I want kids to form? What I want them to learn? And therefore, what are the things that are involving movement that I want to create for them? What sensory motor patterns need to emerge? And therefore, going back, what are the actions and what, how should they be perceptually guided? Basically, what should I build so that kids will come to see and world in order to engage the world, example, right, in a way that are meaningful in terms of a concept such as proportion? What does it mean to engage the world proportionately? What does it mean to move in a new way that is proportionate? So we've, where are we in here? Let's talk about how we should teach, okay, given these points. So technology, here we go. As a design-based researcher, I'm always informed by theory that helps me build design. And then when I evaluate the design, I can update the theory. The design's only as good as the theory and the materials. But then if the design doesn't work the way I want it, then probably I need to update the theory. So I'm thinking of theory and design as kind of co-inscribing. Design-based research, it's conjecture-driven, it's iterative. These are empirical studies where theory and design are co-inscribing. And sometimes we use fancy technology such as that. So we're trying to build various tools for children to learn, to be inquisitive, technologies, want them to be engaged and happy. Come on, slide, pop up. It takes a long time for it to render. All right. Rather than, okay, here's me ad-libbing again. Enter picture of baby, not so happy. Yes, right. So I'll be talking specifically about something called the mathematics imagery trainer, all right? And so what we do is we bring a kid into a room and say, here's a screen, it is red, you have one object here, you can move this one cursor with the left hand and the other cursor with the right hand. Sometimes this is a tablet, sometimes it's remote control. There are various versions of it. We even had a mechanical one to begin with. But the point is it's red. And you move this one up, you need to try and make it green. Kid moves this one up, it's still red, moves this one up, it's still red, moves them together, it's red. Really fast, still red, it flails, and suddenly, whoop, it's suddenly green. Now, why is it green? It so happens that we decided to measure the height of one and the height of the other. And if this height and that height relate according to a certain ratio, like here it's 1/2, it'll be green. That's, I mean, could have decided something else. But here we are training the kids to engage. And we want them to build a new sensory motor perception, a new way of moving that then becomes mathematically meaningful, okay? That's how the talk up to now is coming to a head in this design. Now, once the kid makes it green, we say, can you make it, find another place where it's green? Now, what happens is, as you may guess, especially if you work with kids of middle school, they move their hands this way, okay? Keeping the same distance between the hands, if you will, or adding the same amount on both sides, which, by the way, is the same kind of errors that they make when they first start learning ratio and proportion and fractions, right? Adding the same. 2/3 equals 4/5. I added 2 on both. Don't know why we always use such a voice when we want kids to sound dorky, but they're not, right? So they come up and it's red. And so it takes them time to figure out that, oh, wait a moment. Oh, I see. And then they say to us something, this is like middle schoolers. So actually, the higher I move my hands, the bigger the distance is between them. For us, this is a huge moment, okay? Because this kind of work, it shows us what are the embodied bases of understanding, but then also of difficulty in learning. The schemes they have, the available sensory motor schemes they have are this kind. The kid has never in their life moved this way. Most people have never in their life moved this way. Like if we're holding objects, the objects don't get longer as we lift them, right? And so we are learning to move in a new way, and only then we will make sense of it. We start out with just the grid and within the frame there are these two cursors that you move, and then we bring in symbolic artifacts. So I was earlier having a conversation with some Ames people, and I was talking about the Michelangelo picture of God meeting Adam, and like, here is my stuff. Why should I take it? Oh, this is good for you, but I'm pretty good without it. All right, so enter symbolic artifact. We bring in a grid, and that's a very interesting moment because this is the place the kids have already learned to move in a new way, but that's not mathematics, right? It's not quite. It's like, okay, at the end of the day, where's the math? We need to negotiate. We need to dialogue between these intuitive, eventually intuitive new ways of moving in this case, and the mathematics. When we bring in the grid, something weird happens. The kids who've been moving in a continuous space are now in a discrete space. They've been using qualitative language to say, oh, the higher this goes, the higher it goes, the bigger it needs to get. They're talking about the distance, right? The higher you go, the bigger the distance. But now when the grid comes up, they kind of hook onto one place and then they move other, and they say to me, oh, for every one I move here, I need to move two here, right? So 1 and 2, 1 and 2, 1 and 2. And then next we bring in numbers, and they figure out the multiplicative relations, then we go to other ratios. I want to stay with you, yeah, and eventually we bring in like ratio tables that they use in order to, we say, okay, now you can no longer manipulate, but we're going to use a ratio table. But I want to stick with you at the earlier stage. I want to stick with you at that moment where they first learned to move in new ways. I won't go so much into that. We have lots of this is a project that's been running for 10 years now. We've been studying the way they make sense, initially trying to move this way, then figuring out that, then with the grid, going A per B, and then noticing the multiplicative. I want to skip ahead and talk to you about something we call the attentional anchor. Now, what is this thing? Okay, I'll just skip to here. And should I show you some? People love seeing video, but just in the question of time, I think I'll move ahead. For us as theorists, what most grabs our attention, okay, this is going to take ages because it's trying to render the video. So I see there'll be no video today, but that's absolutely fine. Okay, I think, yeah. So what I want to do with you guys is to speak about this moment, which for us is a giant step for mankind, the moment where the kid first notices, oh, wait a moment, oh, the higher it goes, the bigger it needs to be, because they've come to see the world in a new way, like my dad seeing the world underwater, like seeing a duck and then saying, oh, it's a rabbit, like grabbing the pencil one way, suddenly, oh, I need to grab it in another way to do something else. I want to talk about this moment where this thing comes to the fore, and this is really captures the essence of the work we've been doing in the lab for the past maybe 8 years now, focusing on this moment and characterizing in various ways. We call this thing that the kid comes to, the coming to see the world in a new way, we call that an attentional anchor, seeing the world in a way that they've never seen before, right? And for us, it's really important. And I want to kind of convey this to you. So I have a little exercise that I want to do with you. And okay, so it goes like this. I'm going to split the room kind of in, okay, kind of here, okay, in the pole. So, all right, there's you guys, and there's you guys here, all right? right? You're into it. It's going to be a bit dorky, but okay. So what I'm going to do is I want to give you a kind of first-hand experience of what an attentional anchor is. So I want to show you how something you're not able to do, just like that, and then I'll give you a clue, and suddenly things will fall into place. All right? So what I want you to do is I'll start with you guys here, and you're going to beat with your left hand on the table, and I'm going to beat like this, and for every one that I do, you're going to do 2. So you're going to beat like this. 1, 2, and don't rush. 1, 2. A bit louder so we can hear you. Thank you. Okay, so you know how to do this. Thank you. Yeah, and now with you guys, I'm going to do the same beat, but what I'm going to ask you to do is with your right hand to snap. And if you don't know how to snap, that's okay. Just knock with your pen, because I need it to be a different sound from the beat. All right. So I'm going to do the 1, and you're going to go 3 times this. So snap, 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 snap. Don't get faster. Okay. Thank you. So thank you. So now I'm going to do this again, and I want you guys to do the 2, and you guys are going to do the 3. All right. So here we go. 1, 2, 1, 2, 1. Snap, 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 snap. Okay, this is sounding good. Now, those who are doing 2, add the 3 in your right hand. Those who are doing 3, add the 2 in your right hand. No. Forget it. Okay. And that's kind of weird, because you're able to do the 2, and because if each one of you is a sample of the other side, this population is able to do 2. This population is able to do 3. This population is not able to put the 2 of them together. Now, wouldn't it be cool if I gave you some magical thing that could help you do it? All right, so this is probably going to be the weirdest moment in any talk you've ever attended in your life, because who's going to help us do it? Anybody know who this is? This is a Fresno hero. His name is James Van Hoften, astronaut. I had to find him online. I won't tell you who popped up as the most famous person from Fresno. Yeah, you don't want, let's just say she had to change her name when she entered that industry. That's in terms of clicks, I guess. But why is he going to help us? How is he going to help us? Well, it's not about what he did, it's actually about his name. So have people done karaoke before? What we're going to do, we're going to look at his name, and I hope this thing works. I may have to do it without it. Yeah, we're having trouble with the projection today. So let's just see if this works. So I want you to chant with me his name this way, saying, yes, okay, this is not working out. So I'll have to do it. So say with me, James Van Hoften. 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 Now, why is this going to help us? When I say James, I want you to do both James, then Van Hoften. James Van Hoften. James Van Hoften. James Van Hoften. Wow, look at you, beating 2 against 3. Faster, Van Hoften. James Van Hoften. Excellent. All right, now why does this thing work? It works because you need to do 2 against 3, so I chose a structure that has, I needed to divide the time, the period, into 2 and into, both into 2 and into 3. So I divided it that way, and I found the least a common product of 2 and 3, which is 6. And then I divided, so like James Hoff, James Hoffen, James Van Ten, but together James Van Hoften. So that is how it works. All right, so we're getting even more backlog now. So just imagine, what would it be if you wanted to do 3 against 4? Now for 3 against 4, we need even James Van Hoften cannot help us. We need someone even more famous from from Fresno, and I was told that one of the most famous people from Fresno, and I'm really ad-libbing now because it's just not happening, is, well, do you know her? Where? Maybe my sources are all wrong. Yeah, okay. I need a middle name also here. So this is Audra Ann McDonald. So for 3 against 4, so let's try our karaoke again, okay? So it's just not coming, but it's going to be like this. Audra Ann McDonald, Audra Ann McDonald, Audra Ann McDonald. Oh, there we go. Audra Ann McDonald. So it's like this. Audra Ann McDonald. Audra Ann McDonald. Audra Ann McDonald. There you go. 3 against 4. Excellent. Okay, very good. So why does this thing work again? This time for 3 against 4, I had to choose, of course, 12. And okay, so I'm going to have to be a bit creative here because the slides are not moving. So what I'm talking about here is an attentional anchor. I've introduced a new structure into the environment that wasn't there before for you. Just like the kids had not seen this object, but then suddenly they saw it. Suddenly it was present for them, and that enabled them to move their hand in a new way, saying, okay, this thing here between my hands, the higher it goes, the bigger it needs to be. I can do that. And of course, there's no real thing here, as magicians say, right? There's nothing really here, but that organizes their action. So that's the idea of an attentional anchor. And what I'll do now, because it's just not moving, let me skip way ahead. So meanwhile, I started working with collaborators in the Netherlands, in Utrecht. Waiting for the slide to come up. You know what? I wonder. Let me just do an experiment. Let me come out of this and then try to bring it up again, and see if that does something. No, I think it's not doing anything. So I started collaborating with folks who do eye tracking. Okay. Now, eye tracking is a very interesting methodology. Okay, do I need to bring this up again? I don't know now. It's not up at all. Am I still here? I believe I'm still there. So, okay. So eye tracking is a very interesting methodology. It enables you to see where okay, it's like 30 seconds behind. It enables you to see where people are looking. So like if I were looking at my hand now, it would make like a little orange dot here. And then if I look there, the little orange dot is there. So as I'm looking around the screen, you could get this kind of overlay. You see what is Dor seeing, like through a GoPro. But then you can also see where exactly I am looking at within that scene. So it enables me to see where children are looking. And okay, technology gods are not smiling on me. So I was hoping to show you data of this. So let's see if it works. So I'm skipping slides. I want to talk to you about a design where we ask children to move their hands not in parallel, but not in parallel, but orthogonally, kind of this way. So one hand is moving, so it's not this way now. We've collapsed one of the hands that had been moving up, and now it's moving there. And we ask it, can you make the screen green? Right now, the orange dots show us where the kid is looking, and the thin line shows us the path from one place to the other. So for example, now you can see, let me bring down the light a bit so you'll see this better. You can, thanks, Steve. What you're seeing here, thanks, is, and it's continuous, not jittery as you're seeing here. You can see that the child moving their hand, and you can see where they are looking. And initially, they will look only at their fingers, but then at some point, you'll see they start looking at other places on the screen. Now, why the heck would they want to look at another place on the screen? Well, it turns out we asked the kids, so why, you know, how are you doing this? And well, I'm not getting volume now. Okay, it doesn't matter. It's in Dutch anyway. It's Dutch to me. So the kid says it remains in a line, and she says like, yeah, okay, fine. Turns out she didn't really understand what he was saying because she didn't have access to the eye tracking data. But then later, we asked the kid, can you show us? Okay, so can you try again? And this is what we start seeing. Notice the kid is looking not necessarily at their hands. Instead, they are looking. You'll see the kid is looking more and more in a place on the screen that is not on the fingers. And it turns out that when the kid said, "I'm looking at the line," this kid invented an attentional anchor, which was absolutely striking. What he's doing is he's looking at a diagonal line. I'll do it here. A diagonal line between the fingers. Okay, this is a line connecting the two fingers, and he figured out that if he can make it green, now the moment it's green, he's going to keep this diagonal line at the same angle all the time. I don't know if you can understand what I'm saying. So if you look between my fingers, there's like a diagonal line between. And he says, I'm going to move this line sideways. And if I move it at keeping the same angle all the time, it will remain green. Okay? And we saw it over and over with kids. In fact, we saw all kinds of patterns of the way of the eye tracking of where they were looking. So this is showing us this is where the hands are, but this is where they're looking. One kid, a group of kids were completing a rectangle, and so they're not looking at the fingers. So this means that we were seeing through eye tracking, seeing the very moment when a new sensory motor perceptual structure is born, a new way of attending to the world. And they do that just like with the Audra and McDonald, and just like with this object, they do it spontaneously because this is enabling them to solve the problem of coordinating the two hands in this case. It enables them to couple with the world. It's an imaginary structure that emerges kind of out of nowhere spontaneously as a means of engaging, in this case, in the activity with the tools in order to get the thing green. Getting the thing green here for us is like a parable of doing anything in the world, and in particular doing things that require mathematical forms of reasoning, because we have introduced an embodied interaction. I said earlier, it's a natural user interface, and we deliberately make it difficult for them to do that because we want them to experience this moment where suddenly, oh, I get it. I see the world in a new way. Seeing the world in a new way is the moment of mathematics learning. Fostering opportunities, occasioning opportunities for children to come and engage with the world in a new way is the moment of learning. It's the moment where you figure out a way of looking at the world, a way of engaging with the world that enables you to do the stuff that you care about. And that is the moment of learning. And so let me maybe end off here. Okay, where's my mouse now? Here it is. These forms of seeing and engaging with the world turn out to be conducive to mathematical structures. For instance, the kid who is moving their hand all the time and all the time looking at keeping this triangle firm, it turns out the eyes are going along a trajectory which is equal to, y over x, half, y equals half. The very trajectory of the eye is tracing a mathematical function. Or other kids who were looking at it, who were completing the rectangle, the proportionally growing rectangle, spontaneously doing that. Kids who didn't even know what a Cartesian field is, who had never actually worked with that, they're inventing a different kind of function, but it's continuous. So we were able to capture and characterize these overlays, and then later, what this means is that a teacher who works with a child, where the teacher already knows what are the things that the child is likely to do, the teacher can now speak to the child about these imaginary objects that are like a screen. Between me and the world, there's this diagonal line. I'm moving the line. And we claim that teacher and student talking about imaginary structures is absolutely what we need. That is mathematical discourse. Mathematical concepts, mathematical objects are imaginary. And we, through the eye tracking, are finding how the children are engaging with the world, and we're giving teachers new tools for them to engage with the children in this talk about this imaginary world. And I'll maybe end up with this slide, just to give you a sense of where this kind of goes and how so what you're seeing here is a piece of paper, a sheet of paper that is laid onto a tablet. So the black around is the tablet frame, but the thing in the center is that we just kept everything as was with the eye tracking. And we said, okay, let's see the same game as on the iPad. So this is now a triangle that you could move. So again, this is paper. And we say, well, how would you build the next one? So what you're seeing is a transition from the embodied interaction work to something that, you know, folks would recognize as closer to what people usually do in classrooms. Traditionally, is work with paper and pencil. And we wanted to see what kind of transitions we have between the two forms of work. And what you'll see is the kid starts using measurements, copying parts, and speaking in terms of quantities. So that's where a lot of our work is focused, is on this place, like limbo area where we're moving between the liminal area, moving between the media, but carrying the same kind of ways, the same kind of perceptions. And I'll probably end with this here, but just to say that in other work we've done, we have now what's called dual, like two, eye tracking with both the teacher and the students. We've published on that, when the teacher and students are both looking at the same objects, and we can discern the moment within the zone of proximal development where the teacher makes a little nudge, little move, and suddenly the student starts looking at the same object like the teacher. And I had other slides which I will not show today. You can imagine this has been going on, you know, for some years. Other mathematical concepts such as trigonometry and recent work on algebra, etc., which I will not go in now. I think this could probably be a good time to switch over to hearing questions. Maybe I'll just end with a kind of a conclusion slide, so we'll have that lying there. And as I promised, where's the mouse? Come on, Mr. Mouse, here you go. Right. I said I will bring back the slide I began with eventually, but so conclusions. All right, is this going to work? Yeah. So mathematical concepts are grounded in the sensory-motor perceptions that emerge as practical solutions for the efficient enactment of ecologically coupled movement. So this is what we're talking about, mathematical concepts. Math comes from, I can use this, are grounded in the sensory-motor perceptions, the new ways of seeing. Now, where do they come from? They emerge spontaneously as the kids' practical solutions for the efficient enactment of situated or ecologically coupled movements. So that's what we're demonstrating. And then working with the teacher, the sociocultural reframing of these sensory motor perceptions occurs through the timely mediation of symbolic artifacts. You bring these things, you offer them as alternative ways that may enhance the way children are relating to the world. And students adopt these artifacts spontaneously as readily available means of enhancing their goal-oriented actions. Yet, in doing so, they appropriate heritage conceptual systems that enable them to participate in the social enactment of mathematical practice. So us, the educational designers, we can engineer and facilitate this process to help children to see the world in a new way. And as I said, I bring up this slide from the beginning to see if it makes sense now. Mathematical concepts, such as proportionality, are grounded in the sensory motor perceptual structures, like that thing, that emerge spontaneously as pragmatic solutions to the problem of efficiently enacting ecologically coupled movements. So thank you.
Just have a few moments for any questions or comments or feedback from George, and just open that to the floor.
Yeah. What is your name, please, sir?
I'll bring you this just so our online people can hear as well.
What is your name, please, sir?
My name is Mario.
Mario.
Yes. I was just curious, like, how can we incorporate this information in our classroom and teaching our students? I didn't know what the main connection you were going for, how I can utilize this tomorrow in my classroom.
Yeah. So design-based research is research not so much of what is today, but what could be in the future. We need to do this work in order to figure out what are new directions of instruction. And a lot of it is around developing new technologies and tuning the theory to the products. We are currently engaged in a number of studies where we look to see these kinds of connections. In order to use this in the classroom, you'd have to have the object. We have a free downloadable apps of these things. I didn't show it, I was skipping slides. And that teachers can incorporate already today. We have, currently we're working on here we go. Proposals to use this in classes of special education as well. In particular, we're looking to implement it in, here we go, classrooms of, inclusive classrooms of blind and sighted students who will be using a certain version of this that gives haptic feedback. But this is, yeah, this is available for download already now. We've done some classroom work along it. As I said, I can't show all this stuff, but here are kids working with this. And again, I'm sorry, the sound is not working, but you see how they are working together, so some of the times we have people work together, and then we look to see how mathematical language emerges spontaneously as their pragmatic means of coordinating this collaborative co-enactment of the movements. So these things take time. Work is being done. We have work done now on, I think, 4 or 5 continents now, developing these kinds of tools for all kinds of concepts. But I guess it takes time to hone the message, and also to get the tools just right for classrooms. And also we need to do professional development, to show how to use these things. So it's like a systemic endeavor, and we hope these things will come into our regular curricula. Yes, Karen.
I'm sorry. I appreciate the technology part of your Venn diagram, but I'm more interested in the model of the brain before the computerized brain that would suggest that the quantitative reasoning is more embedded in nature than the need for technology. So as you look at toddlers, is it breaking an orange into, where is the indigenous non-technology that begins the reasoning that underlies this brain structure that you're trying to re-trigger with the technology?
So excellent question, thanks. Karen, right?
Karen,
yeah. So one thing to say is that when we can speak about technology more widely. I mean, we could speak about material artifacts, but we could also talk about various sociocultural forms, even like language. So it's an artifact, it's a way of thinking, it's a way of communicating. We see that even primates use tools. They might take a stone to knock on something, take a stick to hunt ants. But you can think of it as a hammer, as a stone with a stick. We are looking to see how we can engage children with cultural forms. If we just leave them with their own intuitive ways, children who grew up in the forest, so to speak, they will have certain capacities, but they may stop there. What's unique about humans is the wide variety of tools that we have, and the enculturation of the young into adopting these tools. As Vygotsky spoke about how children participate in the social enactment of cultural practice. You give them they're eating with their hands, you give them a fork. So like initially they're not sure what to do with that. I've seen kids, okay, they hold the fork, but then they eat with their hands. Or even better, they take the thing with a fork and then bring it to you and eat with their hand. They need to learn how to use this thing. They need to appreciate how this thing we're giving them somehow extends their capacity to just eat. And maybe initially it doesn't. Maybe it's just it's developmentally inappropriate, or it's just not giving them what they want. But with time, they come to appreciate and use that. Adults use that forks in all kinds of ways, right? So we're looking to characterize what are these pre-technological or intuitive ways of relating to the world, seeing the world, being able to do things. And then how can we intervene with that in order to shape it, form it in ways that take it towards eventually mathematical concepts. And that will come when we introduce various tools. Children learn to move in a new way, but it would remain only that unless we bring in the grid now, which initially they see as having certain attributes like the horizontal lines, enable them to hook onto a place and hold it there stationary. Okay, I know where my hand is. Then they move the other hand to a line. And before they know it, they're moving and they say, oh, for every one I move two. I'm moving one per two, one per two. So that means that we introduced these symbolic artifacts. We didn't tell them what they're about, but the children recognized in them potential utilities for doing better what they were doing before. And we find that tools enhance actions along three dimensions. Children speak about it either enhances the enactment, now I can do it better, or it enhances the evaluation, oh, now I can see if I was right, or it enhances the explanation. Well, now I can tell you what I was doing. So again, we find ourselves lots of E's here. So it's enhanced the enactment or the explanation or the evaluation. And so they appropriate these tools because they see them that they're helping them. In my publications on design frameworks, I speak about the moment where children choose to appropriate the mathematical way of looking at the world. And I speak about this kind of parity or matching that they find. Either they see, oh, yeah, this matches the way what I saw intuitively, but it gives me more precision. Or, oh, this matches the way I was operating before, but it enhances it, but it's the same function. So either I have the same inference or the same function, but I can even do with it more. So like with a hammer, I can do more than just with my hand. It hurts to knock things with my hand. So I can knock things even harder, at least as hard as before, but even harder, and it doesn't hurt me. So that's what we're looking to do, to recognize that moment where they are hesitating, they're in this limbo of why should I, oh, I see this helps me what I was doing. But the key is that they've already been able to do something before. It's not just dictated top down. Here are things, here's a thing called algebra, this is how you do it. But no, here's some kind of problem. Let's see how far you can get with it. And until, it's too much. All right, let's see if this thing can help you. And looking to characterize as researchers to model that very moment, that negotiation between the intuitive and the cultural. So I'm not sure I got at your answer. Yeah, Richard. Yes.
I'm just curious. I know that that Thompson has done a lot of work following what he did with Varela and Rosch with consciousness and awareness, or consciousness awareness / awareness. And I'm wondering if that plays into what you're finding with students, if the things that they're seeing. You know, I know that some of that comes out of meditative and all of that, but I'm just wondering in this kind of a setting, if consciousness, which is something that comes up in this setting and didn't come up with cognitivism, for example.
Yeah.
Does that, I don't know if
absolutely.
that makes sense, but I've just been reading that and that just occurred to me that there's such an emphasis on that.
Thank you, Richard, for that question. So in my work, I collaborate with all kinds of practitioners and researchers and philosophers and people outside of sort of mathematics education per se. I work with sociologists of sports. I work with people in Feldenkrais methods. I work with people in contemplative practices such as yoga. I work with dancers. I publish with these people because we look together at the same kinds of issues. And I published 2 papers with a philosopher of consciousness. And we also held workshops where we were using meditation and Feldenkrais. And actually we did Qigong as well. We're currently studying the metaphors used by Qigong teachers in order to bring people to see the world in new ways. We're writing a paper on how that relates to the science of energy and what it means to talk about energy and what are the metaphors that are used and where they come from. And so we have a paper in the Journal for the Learning of Mathematics, which I published with Patricia Morgan, the philosopher who uses art in meditation. And we say there that this whole movement of mindfulness that are coming to schools, that it's only beginning to scratch the surface. So far, mindfulness has reduced children's anxiety to mathematics, and it has increased their focus, right? But the mindfulness people haven't spoken to much. I think we're the only lab where the mindfulness and the content learning are speaking together, all right? There's a lot of interest in this now worldwide in how to make these things happen. And what we find is there's a certain shift, like the exercise I did with you with the pencil, there's a shift in attention where you suddenly realize my own sensory motor orientation towards the world. So I would say that is probably the kind of Archimedes point where the place we can make the most difference is by bringing students through mindfulness to an awareness of their own consciousness as they are thinking mathematically, in order that they come to realize that how they are seeing the world is just one way, that there could be other ways, and how the student next to me or somebody else or the teacher here, that's also a possible way, and it's legitimate. So that's why I told Mario before that it's a systemic issue, because we need to work also on professional development. We need to change the whole, as I was telling my colleagues at Ames earlier, the whole epistemic climate. I have a colleague who calls it the epistemic climate, meaning in a classroom, how do we talk about knowledge? What is legitimate as knowledge? What is legitimate to talk about in classroom? If I say, well, I'm thinking about algebra and I'm kind of trying to understand how this quantity, and you start using all this florid language and metaphors, are you allowed to say that? And I think you should. And in fact, that's what professional mathematicians do. They're all the time talking, if you look at them, gesturing in the air, trying to understand how things are related, as we saw Terence Tao. He says, I didn't go on with his quotation, at one stage he got down on the floor and he was rolling over, trying to understand something. And then he kind of quips, he says, I didn't put that in my book on the partial differential equations, but that's how I think. So yes, so the work of, so I would say that Evan Thompson should speak to Patrick Thompson. Should have a family reunion.
Okay, I think we'll stop there. Dora, thank you again for a fantastic presentation. Appreciate it.
Thank you.
Just like to, again, thank everyone for joining us tonight. And I also want to highlight 2 more conversations this fall in October, on October 7th. Aileen Rizzo here from the Ames Center was partnering with an art teacher at Sunnyside High School to bring a talk to us that is entitled The Symbiosis of Art and Mathematics, Harnessing the Power of Integration to Produce Greater Equity. So we invite you to join us again at 4:30 on Monday, October 7th. And then in November on the 4th, Ali Hansen will be joining us. She's Assistant Professor of STEM Education at Fresno State to talk about science teacher education and creating expanded learning ecologies through community engagement and research practice partnerships. She'll have an element of making from what she learned from interacting with children and teachers in maker spaces that can contribute to STEM learning. So I invite you to join us for those. Thank you very much for being here. And thank you again to Dora, and hope you have a wonderful evening.